sir, you can click on three dots.
Okay.
So there is an option like of whiteboard.
Oh yeah. Okay.
So if you click on that, then I think
It says start a new whiteboard or choose from drive.
yeah.
Um,
So if you click on first option, then
okay. Start a new whiteboard. Starts Jamboard. But this is not my iPad.
oh
Actually, it is a new Jamboard. So tab the screen more. Start broadcast. Okay, so present during the video meeting. Maybe I can join with the I think I try to join using my iPad. Yeah. Think can you hear me?
Yes, sir.
yes.
Can you hear me?
Yes, sir.
Yeah.
Yes.
And can you see the screen?
Board? Yes, sir.
Yeah.
Yes, sir.
Wonderful. Wonderful. Okay.
So can we begin then?
Yes, I guess we can begin.
Greetings and salutations. Mathematics is in its own way a poetry of logical ideas. So come and let's try to contemplate this poetry. After a very long time, I welcome each and every one of you on this virtual platform. I am Swechha Chulal of Sikkim University Mathematics Department, and I'm honored to be the host. Today, ladies and gentlemen, we've gathered here being honored to listen to Dr. P.A.S. Sri Krishna. He is the Assistant Professor of Mathematics Department in IIT Guwahati. Sir, we are very much delighted to have you in this platform today. His, uh, his research interests are low dimensional topology, hyperbolic geometry, and hyperbolic manifolds. But today, we are here on this invitational talk on group actions, a topic which we shall be very much delighted to hear. And without further ado, I'd like to hand over this platform to you, sir.
Thank you very much, Sweksha, and good evening to all of you. So I thank you all for inviting me to give this talk. I hope that you will have good takeaway from this talk today. So without further ado, let us start this talk on uh, group actions. Group actions. So, first of all, I will sort of assume that, I'll assume that you all know what the definition of a group is, okay, and that of a subgroup is, okay. I understand that there are also undergrad students here, okay. So, if you have any question, you can stop me during the talk, you can ask, you can raise your hand, and one of the moderators will be, pointing it out. So I will assume that you understand what a subgroup is and what a group homomorphism or an isomorphism is, and I will be a bit bold and also assume that you know what a vector space is, what a linear transformation is, and what a linear isomorphism is, and even assume perhaps that you know what the definition of a metric space is. Okay. And maybe you heard of topological spaces even, but that's, when the time comes, I will try to point that out. Okay, we'll stick to very basic spaces so that it, this talk is, everyone can get something from this talk. Okay, so that's the goal. So we will talk about group actions, but first let us talk about groups themselves. Groups, we see them. They first appear in mathematics, even historically, as groups of symmetries of perhaps geometrical objects. So appear as groups of symmetries of geometric objects. Okay. And people understood the importance of these group of symmetries, and not only did they consider geometric objects, eventually they generalized these group of symmetries for algebraic objects, and then other mathematical objects which have various structures. Okay, so we will we'll exemplify them one by one, but first let us look at how these appeared as group of symmetries of geometric objects. So you all might be familiar with this example, but let me still present this example of a dihedral group. Okay, in particular, we will consider the group of symmetries of this particular triangle. Okay, so here is an equilateral triangle. Okay, and it's a dihedron. The word hedral means that it pertains to a head or a face, and dihedral means that it has two faces. So the top face and the bottom face. Okay, so like my hand and the back of my hand, there's a triangle here, and then there's a back side of it. Okay, so this, when we will label this triangle as ABC. Okay, the vertices as ABC. Okay, and it's a geometric object. It's an equilateral triangle. All the three sides are equal, and it's a part of the Euclidean plane. Let us assume that. Okay, and then the back side of when I flip the triangle to the back side, I will name the labels will be A prime, B prime, C prime, corresponding to A, B, C, etc. Okay, so suppose I take this ABC. what are all the ways in which I can pluck this triangle from the plane and place it back as it is. Okay, so you all agree that I can pluck it out from the plane and place it as it is. Okay, or what I can do is I can pluck out the triangle, rotate it by 120 degrees. Okay, so 120 degrees. Okay, so what that does is it brings B to C, A to B, and and then C to A, right? So if I do this 120 degrees, so let me basically do the 120 degrees in the clockwise direction. So like that. So that will be 120 degrees turn. So A will go to C, C will go to B, and B will go to A. Okay, so the vertices permute in a certain way, and then I can put the triangle back in its place. Okay, so what I can also do is a 240 degree turn, and in which case A will go to B, right? So it will turn to 40 degrees. So it's a further 120 degrees turn. So A will go to B, and B will go to C, and C will further go to A, like that. Okay, so I will denote the 120 degree turn by R120, standing for rotation by 120 degrees, and R240 to mean 240 degree turn. Okay, and let me take R0 to be the rotation by 0 degrees, which means I just don't do anything to the triangle as it is. I keep it as it is. Okay, now these are not the only symmetries of this, right? There is also this sort of reflections. Please bear with me as I draw this triangle. Okay, and then there are these axes that I can draw. So, okay, and then this. Okay, so there are these three axes. Let us label the vertices A, B, C, and these particular altitudes or the medians in this case for an equilateral triangle, what you can do is you can flip them about any one of these three axes, and you still get the same equilateral triangle which you can put back in place, right? So let us denote by FA, FB, and FC the reflections of this triangle, about the axes which pass through vertices A, B, C respectively. Okay, so we see that now we not only have these rotations, okay, these three rotations, but also there are these three reflections. Okay, and so totally we have 6 such transformations which take the triangle, the equilateral triangle, and put it back in its place. Okay, so where the vertices A, B, C will go to A, B, C themselves in a certain order, or maybe to the back A prime, B prime, C prime in a certain order. Okay, so if we take a composition of any two of these, okay, something interesting happens, as you all know. So compose this way. First apply FA with R120. So what you are going to do is flip about A and then turn it by 120 degrees in the clockwise direction. Okay, so what happens is that, so first when you flip by FA, what happens is A will stay put because the axis, A passes along the axis, so A is on the axis, so nothing happens to A. But you are now looking at the back side of the triangle, so A prime. Okay, so when you apply FA, you get A prime, and then B and C flip, so you get B prime here and C prime here, unlike C and B here, right? Because you are flipping about this particular axis. Okay, so this one. All right, so you get this one, and then now you apply R120 to this. So you turn this by 120 degrees. So you see that you get this triangle. A prime now is here because you turned it 120 degrees, and B prime now is here and C prime is here. Okay, so this is nothing but flipping about this particular axis, right? Because B stays in place, B becomes B prime. You're now on the back side of the triangle, and A and C, they permute. A goes to C and C goes to A. So this is, so I will write, I'll write FA, and then you apply R120. So when I write like this, first you apply FA and then you apply R120, and this is nothing but FB. Okay. So, you can make these composition rules. You can compute all the compositions like this of any two. Okay, and then you all know the result of this. Firstly, this operation is this composition operation is associative. You might have heard this word in context of groups. So associative, what it means is that if you have R120 composed with FA composed with FB, okay, it does not matter how you apply these compositions. So whether you first compose FA and R120 and then FB, or whether you compose FB and FA first and then compose it with or do R120 first and then compose it with the composition of FB and FA. Okay, so the compositions, they are basically associative like this. Okay, and these compositions, okay, with a small change, I have indicated that the turning is clockwise like this, A to C and C to B. So if it were anti-clockwise, then I have made a small table here. You can see that this is what you get. You can make a table of these compositions. You apply this first. This, here are your first operations. Okay, there's a small change, like I pointed out. The change is that I'm turning R120 here means it's a 120 degree turn in the counterclockwise direction, and R240 is turn in the counterclockwise direction 240 degrees. And first I apply these and then I apply these, then the composition is going to be given by this table. So from this table you can read out first apply FA and then apply R120, you are going to get FC, etc. Okay, so this table, as you might know, is called the Cayley table. Cayley table for this particular set. So set of symmetries of the dihedron. In this case, the dihedron being a equilateral triangle. Okay, so as you might be aware, there are some rules that this table follows. First, you note that the composition of any two of these symmetries is once again a symmetry from this list, from this particular list here. Okay, and each of these symmetries appears in each row and each column. Not only that, each of these symmetries appear in each row and each column only once. Okay, and in particular, R0 appears in each row and each column. Okay, and R0, and it appears only ones. Okay, so we can say that looking at the table, we can point out that R naught composed with X, where X is any of these symmetries, is equal to X composed with R naught, and that is X. So that is evident from the table. By looking at the column or row corresponding to R naught, you see that the column or the row corresponding to R naught is that particular column or row. So it's basically the same row which repeats here, and the same column repeats here, right? So so that's why we can write this rule here that R naught composed with X is X composed with R naught, and then that is equal to X, where X is any of these R naught, R120, R240, and FA, FBS. So R naught, which satisfies this property, we say, and it's unique, we say that R naught is an identity element. Okay, and we see that for every X in, so we should already give this set a name, right? There is the set. So maybe we should call this set D3, standing for the dihedral group corresponding to the triangle, 3 sides or 3 vertices. So if X belongs to D3, there is a, for X belongs to D3, there is a Y in D3 such that X composed with Y is equal to Y composed with X is equal to the identity R naught. Okay, so this says that basically every element has an inverse operation to it. So these elements can be seen as operation on the triangle. So you do one operation on the triangle, and then there is an undoing of that operation. So suppose you turn by 120 degrees, you can turn further by 240 degrees to get back to R naught. Okay, so every element in D3 has an opposite action, and then that is which basically gets you back to R naught or does nothing to the triangle, and hence these will be called inverses. So X is called the inverse of Y and vice versa, right? So we have an associative operation, and then there is, namely the composition is associative, and R naught is an identity element, and X is the inverse of Y. For every X in D3, there is a corresponding inverse Y, and Y serves as the inverse of X. So this is one example of a group that we see. Okay, the very early example of a group that we see. Okay, it appears as a group of symmetries of this triangle. So more abstractly, as you all know, like I said, I'll assume the definition of a group. So a set X or a set G with an operation dot, okay, which satisfies these 4 axioms that first G is closed under dot, which means that, as you saw in the case of the Cayley table for the D3, all the elements in the table are from the set G itself, set D3 itself. So that's closure, and 2 dot is associative. It's an associative operation. Okay, and 3 there is an identity in G. There is an element E in G such that E times G is equal to G times E is equal to G for all G in G, right? That's an identity element. And 4 existence of identity and 4 existence of inverses for each G in G. There is a there is another, I mean, not necessarily different, but there is a G bar in G such that G times G bar is G bar times G is the identity element. Okay, so a set G with an operation dot which satisfies all these four properties is called a group. G dot is a, okay, so that's the definition. And sorry, yeah, so these groups appear as symmetries of geometric objects like D3, and likewise you can take any regular tetrahedron, or you can take a dihedron itself. So suppose you take a hexagon, regular hexagon, you can compute all its symmetries and then make a table like this, the KLA table, the so-called KLA table, and see that all these four axioms check out for compositions. Okay, so hence the symmetries of any geometric object actually form a group. Okay, so it need not even be a regular one like that. Okay, so it need not necessarily be a regular polygon like that. You can take the symmetries of any object, geometric object, and the set of all symmetries automatically forms a group, which basically means that it checks out all these four properties. Okay, so that's a group as a group of symmetries of a geometric object. Okay, so but groups also appear as symmetries, like I announced, symmetries of a more general kind of objects. Okay, so let us see, let us look at a set. So next example is that of a set. So take the set A, B, C, a 3-element set once again. Okay, so when we consider a set, the natural function from a set to itself is going to be a bijection. So consider a bijection F or phi from, so let's name this set S to S. There is a nice diagram that we can draw, a Venn diagram containing this set ABC, and then we can draw a function to be, a relation. We can draw arrows from the set S to itself. So maybe a function phi is like that. That's a bijection. It's a one-to-one onto function like that. Okay, so this is an example where every element goes to itself. Okay, so we can call this phi naught, and we know that we can write relations using ordered pairs. So in this case, let me write phi 0 is AA, BB, CC. Okay, and then that's one bijection. So this describes a bijection. This tells that A is mapped to A by phi naught, B is mapped to B by phi naught, and C is mapped to C. Right? So we can have other bijections. Let us record other bijections. A is mapped to B, B is mapped to C, and C is mapped to A. Phi 2 is another bijection, which is A maps to C, B maps to A, and C maps to B. Okay, we can have more bijections, and how many after all will we have? We can have 6 bijections like this. So A is mapped to A, B is mapped to C, and C is mapped to B. And phi 4 is A is mapped to C, B is mapped to itself, and C is mapped to A. And phi 5, this is A is mapped to B, and B is mapped to A, whereas C is mapped to itself. So the picture of phi 5 once again is ABC, ABC, C is fixed, C is mapped to itself, A and B are interchanged. Okay, so if we consider the set of all these bijections, we write these as S3. These are phi naught, phi 1, phi 2, phi 3, phi 4, and phi 5. And S3, so when you take two bijections, you can compose them. It is still a bijection from the set to itself, right? And these 6 elements basically, form a group. S3 with composition, under composition, forms a group. And its KLA table, you can once again prepare a KLA table, phi naught composed with phi 1. For example, phi naught composed with phi 1 is going to be phi 1 itself, etc. Okay, so you can basically form a KLA table, and its KLA table is going to be exactly this. Okay, so with R naught replaced with phi naught, R120 replaced with phi 1, etc. So if you replace these with phi naught, phi 1, phi 2, phi 3, 4, phi 5, etc., also on the top row, then the KLA table of S3, the group S3 under composition, is going to be exactly that. Okay, so it so happens that it is exactly that. Okay, so excuse me. So this is like the vertices of the triangle. So ABC behave like the vertices of the equilateral triangle, and this bijection can be thought of as, turning the triangle. So now here is a slightly abstract set of symmetries. Here is a set of symmetries. In this case, we talk of bijections as symmetries of a set, and the set of symmetries of the set under the composition of bijections, okay, of composition of the symmetries forms a group. Okay, so groups appear as symmetries of geometric objects. Now, in this case, they appear as symmetries of a set, more abstractly, the symmetries of a set. There are other contexts in which groups appear as symmetries. Okay, so here is another context in general. So I will write that groups of symmetries of objects in any category. Self-symmetries. So I will write self-symmetries of objects in any category. Of course, I'm not going to formally define a category, but I will one by one pick the category and then just directly give you the self-symmetries. So first we saw in the category of sets, for example. Okay, so in the category of sets, we have, let X be a set. Okay, so let X be a set. The set of self-symmetries, in this case, in the category of sets, the set of self-symmetries, i.e. These are bijections, self-bijections of X, form a group. The self-symmetries form a group. Okay, so written in a certain way, well, written in a set format, we write odd X to denote the, so when X is a set, odd X denotes the automorphisms. They are the self-symmetries. Automorphism, the word automorphism means self-symmetry in category theoretic language, but we'll just say that these are self-symmetries for the uninitiated. So this is odd x is set of all bijections from x to x is a bijection. We just saw in the previous example that if x is a 3-element set, the odd x is a 6-element set, right? So x is the set ABC, S is the set ABC, and S3, the set of all symmetries, is basically a 6-element set. Okay, so of course it's an exercise. Probably you know the answer. Okay, if x is an n-element set, what will be the size of odd x? Okay, but there is no need for x to be finite. You could have an infinite set, okay, and you can still ask for the set of all bijections from x to x. Okay, so what are all the bijections from natural numbers to natural numbers, for example? Okay, and then that will be a group automatically. The set of all bijections from natural numbers to natural numbers will be a group. Why this is a group under what? Under composition, of course. So I should write that under composition. Composition of bijections. Okay, and that will be a huge group. Okay, so that is in the category of sets. Okay, so an example is previous example. Example, previous. Example of S is equal to ABC and odd S was the group S3. Was the group S3 under compositions. Okay. So next we can look at another category, namely the category of vector spaces. So I'll use the same letter X to denote a vector space now. So vector space, a vector space over a field comes with a certain algebraic structure, right? You can scale vectors and you can add vectors. Okay, so and of course any composition of this, you can scale vectors, add them, and again scale the resultant vector, and you can keep adding other vectors, etc. Okay, so these operations are called taking linear combinations of vectors in a particular vector space. Okay, so you might have studied linear algebra, and where you encounter these vector spaces, abstract vector spaces, not necessarily Rn, but abstract vector spaces. But however, you can think of Rn if you haven't seen abstract vector spaces. Okay, so let X be a vector space. Okay, so for simplicity, you can think of finite dimensional vector spaces over convenient fields like the complex numbers or real numbers. Okay, so think of finite dimensional vector spaces over R or C or the complex numbers. Okay, so these are like Rn. Okay, is a vector space over R for some natural number n. Okay, Rn over R over the field R. So the scalars themselves come from the field R, etc. Okay, so example of vector spaces, and let X be a vector space. The set of all, so odd X we'll denote by odd X, the set of all automorphisms of X. In this case, they are maps from X to X, which are, what do you think this should be? What should be F? Anyone? Can it be any map? What would you want F to be?
Linear transformation.
So you want a linear transformation. Would that be enough as a self-symmetry of X? Recall?
Linear isomorphism.
Sorry?
Linear isomorphism.
That's right. So for self-symmetry, we don't want the structure of X to be destroyed in any way. So here we took bijections for a set. Okay. In the case of vector spaces, there is linear structure there. So we want F is a linear isomorphism. So we want F to be a linear isomorphism. So you collect the set of all linear isomorphisms of X. Okay. Will there be only one? So suppose you take R2, okay, or even R for that matter. Okay, I'll just take R. Okay, what will this set be? Okay, I'll ask that question, but firstly, I want to announce that if you take this one, it's going to be a group under composition of linear isomorphisms. Note that. So I'll erase this part. I'll come to this later. I'll say that if F is a linear isomorphism from X to X, so I will write it above. I can write above. So F is a linear isomorphism from X to X, and then G is yet another isomorphism from X to X. Then I can compose them. G composed with F is also a linear isomorphism from X to X, right? It has to be a linear isomorphism. It won't collapse dimension of X in any way. Okay, it cannot send non-zero vectors to 0. Okay, so it has to be a linear isomorphism, at least for finite dimension. So that's the proof that it has nothing in nullity. Okay, so right. So basically, it is going G composed with F is also going to be an isomorphism, and hence, if G and F are from the set OT X, G composed with F will also be from the set OT X. So this is closed under composition. Okay, and then there is naturally an identity in the identity element in the OT X set, right? So what will be the identity element? Any guesses? What will be the identity element in this set OT X? There is an identity linear transformation, right? There is an identity linear transformation from X to X, which basically takes any element, any vector V to itself. That is going to be the identity, because F composed with identity will give you F of identity. So F composed with identity of any vector V is going to be F of identity of V, which is going to be F of V, like that. And the other way around, identity of F of V is going to be F of V, because identity does not disturb a vector. So this says that F composed with identity is identity composed with F is going to be F itself. So naturally there is an identity map, and then that serves as the identity element of this group OT X with respect to composition, right? So it's closed. It's, you know, this group is, well, this OT X is closed under compositions. There is an identity element, and then there is an inverse as well, right? So if you take an isomorphism from X to X, you all know that F inverse is also an isomorphism from X to X. I mean, there is a inverse operation that you can construct, right? All you have to do is, if you know, how is F inverse defined? It's an isomorphism. F is an isomorphism. So F inverse of a vector V is such a vector W where F of W is equal to V, right? Easy. So that's the definition of F inverse of a vector V. So if F of W is equal to V. So you can only find a unique vector like that because F is an isomorphism. Okay, it's a 1-1 function. So you can only find one vector W such that F of W is equal to V. So F inverse of V is defined to be W. So there are inverses, and these inverses naturally work in this way. F inverse composed with F is F inverse, F composed with F inverse, and that is going to give you the identity on X. Right? So this forms a group. The odd X automatically, it forms a group. So set of all linear isomorphisms of the vector space X forms a group. Okay. So yeah, coming to my question now. So what can you think of the automorphisms of R? So let us take the one-dimensional vector space R over R itself. Okay. So what are the automorphisms of R as a set? Okay. So how big is this set? Let us try to answer this. Or what is this? What is the set description of this? So here is a one-dimensional schematic picture of one-dimensional vector space R. Can anyone give me a non-trivial map, non-trivial isomorphism from R to R? There is identity. By trivial, I mean identity. You can give me identity, but I want something other than identity. Anyone? A linear transformation from R to R.
X going to minus X.
X going to minus X. Okay. So X. So that is correct. Good.
Sir, line passing through origin.
Line passing through origin. Well, we only have a line. So which other line do you mean? There is only a line, right? There is no R2. This line is not sitting anywhere. It is only a line.
From R to R defined by f of x equal to x to 3x.
Sorry, f of x defined by f of x is equal to, this is one example. The second one is f of x is equal to
2x.
2x. Correct? Okay. So f from R to R defined by f of x is equal to 2x.
Next, we can generalize it x f of x equal to x.
I can't hear you. Your voice is breaking. We can generalize it to f of x is equal to
mx.
Where? M is what?
Yes. M is any real number.
M is any real
Not
number?
zero.
Apart from 0. Correct.
Non-zero.
Yes. So non-zero real number. That's correct. So this pretty much describes all linear transformations. Are there more? See, this is a linear transformation.
No, sir.
It's an isomorphism. You can check that it is an isomorphism because it's an isomorphism. Okay, from R to R. How do you check that? F of alpha x plus beta y. Firstly, this is going to be alpha times m times alpha x plus beta y, which is going to be alpha times mx plus beta times my, right? So this is going to be equal to alpha times f of x plus beta times f of y. So it's a linear transformation. Okay. Further, what is the kernel of this? If f of alpha x plus beta y is equal, sorry. If f of x is equal to 0, then mx is equal to 0. Okay, for some m is non-zero real number, recall. We fixed a m non-zero real number. So mx is equal to 0. only when x is equal to 0, because m cannot be 0. Okay, so if f of x is equal to 0, then x has to be 0. So the only element in the nullity is 0. So this means that the kernel of f is just the 0 vector. This means it's an isomorphism, isn't it? Right? So the kernel is just the 0 vector. So this means that this is a linear isomorphism. So for any non-zero real number like this, f of x is equal to mx is a linear isomorphism from R to R. Are there more? Somebody answered no. Are there more isomorphisms than just
No, sir.
no? Can you prove it?
Yes, sir. We got a theorem in real analysis. If it maps from R to R, such that f of x plus y equal to fx plus y, then map to fx to mx type.
Yeah, apart from it being a theorem, I mean, it's perhaps an exercise, an easy exercise to actually prove that these are all the automorphisms, vector space isomorphisms from R to R. Okay, so if you were to ask what is this set at R, it is basically set of all. It is equivalent to set of all real numbers minus 0. Okay, so for each m in R minus 0, we get fm of x is equal to x. Fm is the name of that linear transformation. Fm of x is equal to mx. So the odd R is basically equal to the set R minus 0. As a set, it is equal to R minus 0. Further, we just announced that composition, etc. works, right? Composition is a nice operation on this set. So we now know that odd R is actually a group, and it is the group whose underlying set is R minus 0. Okay, so let us see how composition works. So let us do the composition. Let m comma n be two non-zero real numbers. Okay, so what will be fm of x? This will be mx for all x in R. This is the vector space R. And what is fn of x? This is going to be nx for all x in R. What will be the composition? fm composed with fn of x. This is going to be fn of mx, which is in turn equal to nmx, right? Or mnx, does not matter. Is equal to fm composed with fn of x. It is basically commutative as well. Fn composed with fm is equal to fn composed with fm, or fm composed with fm. Okay, so but the point is that fn composed with fm is the map which is equal to fmn. So this computation tells us that fn composed with fm is the map fmn. Now notice that I have removed that x in R. I mean, that's a functional equation. All this is all this is a functional equation. It is equation of functions, and hence I can write this as Fn composed with Fm is Fmn. In the group, okay, in the group ought. Okay, so in of, okay, so as a set we have R minus 0. The odd R group is R minus 0, right? And how does composition work? The composition just multiplies the indices n and m like that. Okay, so isn't this the same as real number multiplication? N and m are getting multiplied, right? This is the real number multiplication. Okay, so you take elements of R minus 0, each one represents a linear isomorphism from R to R. Okay, and then you take any two of them, the composition is nothing but it is like the multiplication of non-zero elements, well, multiplication of elements in R minus 0. Okay, so this is the equation which highlights that. This is the equation which highlights that. And so odd R is nothing but the group R minus 0 with multiplication. So odd R, the vector space R1, if you take the automorphisms of R1, these are this is isomorphic to, as a group isomorphism, this is isomorphic, this is group isomorphism. This is different from the vector space isomorphism that I am talking here. It's a group isomorphism. Odd R is a group, and odd R1 is actually isomorphic, group isomorphic to R star. You might have seen this symbol R star, which means it is R minus 0 with the multiplication operation, with the usual multiplication of the real numbers. Okay. So this is an example of group, okay, as a symmetry of vector spaces. Okay, the set of symmetries of the vector space R1 over R is actually the group isomorphic to the non-zero real numbers under multiplication. Okay, that's what it is. Now,
can I repeat the line?
Yeah, so the group of automorphisms of the vector space R1, okay, is isomorphic to the group of non-zero real numbers under multiplication.
Sir, R1 means?
R1 means it's the vector space. This one is the
R1. Okay, sir.
Vector space.
Okay, sir.
One-dimensional vector space over R. Okay. Now I can ask you to do an exercise similarly. What will be the group of R2? Okay. But I mean, more than an exercise, it gives you a group that you perhaps are familiar with. Okay, so first give me an isomorphism from R2 to R2. What is an isomorphism from R2 to R2? Linear isomorphism from R2 to R2. How do you describe it? Firstly, what are elements of R2? So an element looks like a vector xy. There's an element in R2. Right? Okay. So what will F do to an element R2? I mean, like this in R2. It will give an element in R2 naturally, but what should be in the first place and what should be in the second place? Anyone? Do you know an example of a linear isomorphism from R2 to R2? Someone can try. Okay, maybe I will give an example. 3x plus 2y and x plus y. Okay, so that's an example of a linear isomorphism from R2 to R2. Well, why is it an isomorphism? I need to prove it, but this can also be written as 3, 2, 1, 1. Do you all agree? Times xy. And the determinant of this matrix is non-zero, and hence this is a linear isomorphism from R2 to R2. Okay, so you might have encountered this in linear algebra, that if you take a matrix and multiply it with the vector xy like that, a 2 by 2 matrix, and multiply with the vector xy like that, you get a map from R2 to R2 itself. Okay, so that can be written, yeah. So, and then that matrix, if it has a non-zero determinant, this will be an isomorphism, right? So F is a isomorphism. It's 1, 1 and on 2. Okay, and then 1, 1. So the kernel is basically just the zero vector.
Sir, what R2 is isomorphic to GL2R?
Yes, that's right. So this is so the set of all isomorphisms are basically matrices like this. They can be associated with matrices like this, where the entries are real numbers. Okay,
and
so
non-zero determinant.
Yes, that's right. Non-zero determinant like this. Okay, so matrices with real entries and non-zero determinant. And so you know that this is isomorphic to the group of all 2 by 2 matrices A, B, C, D, such that AD minus BC should not be equal to 0. Okay, and you might have, so this group is called the general linear group of 2 by 2 matrices with real entries. Okay, so I should specify here perhaps that A, B, C, D are real numbers. Okay, so that is a set of all automorphisms of the vector space R2 over R. Okay, so those are all the self-symmetries of the vector space R2. Okay, they preserve the vector space structure. So it's a group. GL2R is a group with respect to matrix multiplication, right? So the set of self-symmetries, what I'm trying to arrive at here is that the set of self-symmetries of R2 or of R are basically groups. Okay, so they are set of symmetries of an object, in this case vector space. We saw earlier that in the category of sets, the set of self-symmetries, they are bijections, and they also form a group. Okay, so that was the category of vector spaces. Now let us slightly go ahead and let's look at metric spaces. Okay, so easy examples of topological spaces. These are metric spaces. Let us look at E2. Okay, so metric spaces. So 3, the category of metric spaces, and more than metric, let us consider geometric spaces really. So let us look at E2. Okay, this is the Euclidean plane. So you have learned high school geometry, and in high school geometry, you work constantly in the Euclidean plane. So you would have encountered theorems like triangles between two parallel lines are always, they have equal area and stuff like that. So there are, you do Euclidean geometry in class in high school, pretty much all of high school, and that is done in Euclidean spaces, and then the distance formula in Euclidean plane, etc. Right? If you take 2 points x0, y0 and x1, y1, you can calculate the distance between them as square root of x1 minus x0 square plus y1 minus y0 square, right? So there is a distance formula, and so the symmetries in this case, which the self symmetries of E2, which we are now calling automorphism group automatically. This automatically forms a group. This is the group of, let me announce that it's already a group of isometries. In this case, it's a metric space. So iso, similar, okay, and then metric. So isometry means that it is.
Sir, Euclidean planes means R2 Cartesian plane.
Yeah. So more than that, Cartesian plane with the usual inner product, the dot product.
Okay,
that
sir.
is, so E2 will mean that. So you have to not only take the naming convention of R2, naming convention being x comma y for the points, you should also take the Euclidean inner product, the dot product. So the jump from here to here comes with the dot product. This does not have a dot product. This has a dot product, the usual dot product. That's the difference between E2 and R2. Okay, so the dot product makes all the difference. It gives you norms of vectors. It gives you angles between vectors, right? So otherwise, if I take x comma y and x1 comma y1 in R2 without the dot product, I can't calculate. I can calculate distances between them. However, I can't calculate angle between the vectors xy to x1 y1 and xy to x2 y2. There is no equipment for angle. You can only calculate distances, right? So here I said geometric objects. So I'm not only considering the metric structure here, I'm also considering the geometry of E2. E2 is the Euclidean plane. And then the group of isometries, the Euclidean isometries, they automatically form a group. Okay, so group of isometries. So can you think of one isometry, the Euclidean isometry, which preserves? So these are group of isometries. These are maps from E2 to E2. These are F from E2 to E2, such that F preserves the inner product on the dot product, inner product or the dot product of E2. So when it preserves the inner product of E2, so let me write this. I mean, I should have written this in a set format. It is set of all F from E2 to E2 such that F preserves this inner product. Such that F preserves this inner product. Okay. So when it preserves the inner product, it preserves distances. It also preserves angles. Okay. So can anyone tell me one Euclidean isometry? An isometry which preserves both angle and distance? That should be easy. Take the Euclidean plane, translate it. Does that preserve angles? Yeah?
X plus lambda, comma y plus lambda, or lambda 1, lambda 2.
Okay.
Translation.
So that's correct. So f of x comma y is equal to x plus lambda 1, y plus lambda. You want to do this?
Yes, sir.
That is also a Euclidean isometry. So it's a translation by a certain number lambda. Okay, lambda 1, lambda 2 being that, ordered pair. So you can actually have a translation by vector lambda 1, lambda 2, not number, the vector. Okay, so this is an example. not only translations, there are rotations. You can rotate the Euclidean plane about any particular point. You just take the rotation. That's also a Euclidean isometry. It preserves both angles and the whole inner product. Okay, so that's another example of isometry. Okay, so then there are compositions of these. So composition of isometries will be isometry, because if you take composition, that will also preserve the inner product. So if you have dealt with inner products, you can actually do that as an exercise. So rotations and reflections, rotations and translations, these generate the isometries of E2, the orientation preserving isometries. Of course, you can reverse the orientation by taking mirror reflections. What you can do is take a straight line in E2 and reflect it about that straight line. It's like a mirror reflection. That will also be an isometry of E2. However, it will not preserve the orientation of E2. That's a subtle aspect, but let's skip that in interest of time. Okay, so the group of automorphisms of a metric space will be isometries. They also automatically form a group. Okay, so far we are able to say that the group of automorphisms, the self-symmetries of not only a geometric object, but also other abstract mathematical objects. In this case, we saw sets, we saw vector spaces, and we saw metric spaces. They also form groups. Okay, so one final example in this direction that I will take is that of topological spaces. Have you seen the definition of a topological space? Is it too alien to you? You can, if you have not seen a topological space, you can think of still metric space like R2 or like C. Okay, the complex plane and R2, the with the usual topology. So these are same with the usual topology. Okay, so topological spaces. And then what are the self symmetries? So if X is a topological space, what are the natural maps from X to X which preserve the topological structure? These are called homeomorphisms, F from X to X, such that F is a homeomorphism. Recall what a homeomorphism is. A homeomorphism is a map which is continuous from X to X. In the case of topological spaces, we study continuity properties when we study topological spaces. So F from X to X is a continuous map and it is a bijection. So recall what a homeomorphism is. If X is a topological space, okay, a map F from X to X is called a homeomorphism if F is a bijection. So bijection means that there is an F inverse as well. F is continuous and F inverse is continuous. Excuse me. So the inverse map is also continuous. So then you call such a map F as a homeomorphism. Okay, so homeomorphisms are more general than the rigid isometries. So for example, I just said that R2 and E2 are pretty much the same except that E2 has the additional dot product. Okay, and in the case of topological spaces, if we take the space R2 as a topological space, what you can do is you can shear and bend the space. So imagine if you might have seen oil spilled over water, it forms all these wavy colored patterns, right? So you can actually bend all of that. So I will give you a more mathematical way to show a homeomorphism of R2. So here is R2, a picture of R2. Here is the x-axis and here is the y-axis. Okay. So what you can do is you can actually, as long as here are some straight lines between, in the first quadrant, what you do is you can take a map F and bend y like that, bend x like that, and in a similar pattern bend all these straight lines so as to cooperate with this bending. Okay, so it's such a very general map like that. As long as it is continuous, it's a bijection, and because it's a bijection, F inverse should be defined. So if you take a point here, it has gone to certain point here, and you should be able to come back from here to here in a continuous fashion. What does continuity mean? It means that nearby points here go to nearby points here. Nearby points here go to nearby points here, and they come back in the same way. Okay, so nearby points go to nearby points, and in such a way that when you go from this, the nearby points are called neighborhoods. If you go from here to here, you can come back from here to here in the same neighborhood. Okay, so this will be bijectively mapped to that neighborhood. Okay, that sort of map is called a homeomorphism. And what I'm going to say here is that the group of, so this odd X, which is the set of all homeomorphisms of a space, okay, to itself, that is going to form a group. So odd X is a group. Okay, so to give you a feel of it, let us look at R1 instead of R2. Let's just look at R1. Okay, and let us look at the automorphisms of R1 as a topological space. Okay. Now, as a topological space, what you can do for R1 is you can actually think of R as a straight line, like a rubber band, okay, infinite rubber band like that. What can you do to put it back in place without disturbing the continuity? Okay, so continuity means that nearby points should go to nearby points. So what you can do is you can stretch it at one place, contract it another place, stretch it at one place, contract it another place, etc. That's one function, and it is a homeomorphism because nearby points will go to nearby points. Another way to do a homeomorphism is uniformly stretch it. So a uniform stretch like that can be described as a dilatation. So f of x is equal to lambda x. Okay, so we also saw that this was a linear isomorphism, but it also serves as a homeomorphism. Okay, so what is not a linear isomorphism but is a homeomorphism is the following. You take f of x is equal to, it's not appearing, I'm waiting for it to appear. So take f of x is equal to x cube. So you all know the graph of this function, f of x is equal to x cube, looks like that. Okay, very, not a good drawing, sorry. Something like that. This is a 1-1 onto function from R to R. Okay. Not only that, if you take points nearby on the real line, they go to points nearby, although it blows off, it blows up like that. x cube. If you take a small interval and compute its x cube, it will be huge. But however, nearby points will go to nearby points on this graph. So this is an example of something which is not a linear isomorphism, but is still a homeomorphism. The inverse of f will look like cube root of x. Okay, so that's a example of a homeomorphism. So this ORT R1 is really a huge group where all such functions are included. It's a really huge group, ORT R. Okay, so it's a huge group. And so, these also form a group. Okay, so groups appear as automorphism groups in various categories. Okay, so now let us return to the setting of the metric spaces. Setting of metric spaces and do an interesting example there to cover the basic goal of this talk, namely group actions. I haven't actually touched upon that. So let us look at the metric space R. It means that I am taking the R with its usual distance measure. So if x comma y belongs to R, how do you measure the distance between x and y? The distance between x and y is given by the absolute y minus x. This is the usual metric on R, right? This is called the metric on R. That forms a distance measuring gadget. So there's a picture also. Here is x, here is y. The distance between these is given by absolute of y minus x. Right? This is the usual line picture of R. So now in the metric space category, I will ask you what are the automorphisms of the orientation preserving automorphisms of R. Okay, so when I say orientation preserving, I mean that R has a direction, right? So if you walk to the right of 0, you will only see positive numbers. And if you walk to the left of 0, you'll see only negative numbers. So I'll ask you that if you transform R in such a way that numbers to the right are bigger and numbers to the left are smaller. Okay, what are the transformations from R to R? Can you give an example of a function from R to R which preserves distances and which is basically a metric space automorphism? Can you give such an example? So we'll come to ORT R in a moment. It's a group of all such functions. First, can you give an example of a function like that? F from R to R, which preserves distances. Anyone?
Add some positive number to each point.
That is good. So f of x is equal to x plus some r. So fix a real number r, fix a real number r, and define f to be f of x is equal to x plus r for all x belongs to r. So what this does is it just basically translates. So I can write this function as fr of x. So r can be any real number. Okay, so there is translation like that. Now notice that there are also reflections of the real line, but this does not preserve the orientation of r. Okay, so let me write that. Well, it requires proof, but these are the only distance preserving maps of R. Okay, so R as a metric space, R is a metric space or a distance space Okay, so R is a metric space. The the orientation, that plus means that orientation is preserved. The automorphism group of the metric space R is equal to translations, all the translations. And how much can you translate by? You can translate by any real number R. So this is equal to R. And then the group, you can compose two translations by adding, the translations. So this is the group R plus. It is the group of all real numbers under addition. Okay. So now there is a subgroup of this, namely the subgroup of integers. Okay. So if you take M, what is Fm of x by this definition that we had? What is Fm of x? Fm of x is going to be x plus m, right? Is equal to x plus m. So these are integer translations of the real line R. So under this map, integers go to integers, right? If x is an integer, this is for all x belongs to R. If x is an integer in particular, Fm of x is equal to x plus m is also an integer. Agreed? So integers move to integers. And what happens to non-integers? None of the non-integers can move to integers, because a non-integer plus an integer is not an integer, right? So in general, if you take any real number x, okay, and let us put an equivalence relation. Let us say that x is equivalent to y. X and y are real numbers. If y is the translation of x, okay, so which means that if there exists an Fm in z plus, okay, Fm in z plus or m in z plus, such that x is equal to, or Fm of x is equal to y, or said otherwise, there exists an m prime in z plus such that Fm of y is equal to x. So we are taking the real numbers and putting an equivalence relation on it. X, if x is translated to y, then we are saying x and y are related. Okay, so in particular, if we take any real number x, x can be written as the lowest integer, the integer which is just less than x, plus the fractional part of x. And this fractional part of x is going to be between 0 and 1. Right? So in particular examples, 1.01 is going to be equivalent to 0.01. 2.3256 is going to be equivalent to 0.3256. Okay, and pi plus 18 is going to be equivalent to pi is equivalent to pi minus 10, because these are all integer translations of pi. Okay, and then this is equivalent to pi minus 3. Notice that pi minus 3 is the unique number which is between 0 and 1. It's the fractional part of pi. Okay, and also 2 pi under this equivalence relation is not equivalent to pi. So these are some examples of this equivalence relation, how this works. Okay, and then notice that every number by this equation, every number is equivalent to a unique fractional part of itself. Okay, but one fractional part represents several numbers. Okay, so every number is represented by, every real number is represented by a number. Hash means a number. Okay, a number in the interval 0, 1. Of course, notice that 0 is equivalent to 1 because the fractional part of 1 is 0. Okay, and furthermore, if you have points very close to 0, you are actually you have points very close to 1 and just greater than 1, so something like 1.01. It is actually close to 0 because it is equivalent to 0.01, right? So these numbers which are close to 1 are also close to here. So if you are closer to 1, you're actually closer to 0. Okay, so you have this interval 0, 1 with the peculiar property that the equivalence has made 1 equal to 0, and if you're closer to 1, you're closer to 0. So that means that you have to take this interval 0, 1 and attach it at that point. 0 is equivalent to 1, so you get 0 is equivalent to 1. So the set of equivalence classes under this equivalence relation is going to be a circle. So this is called the action of Z. So we took the group of R plus the group of automorphisms of R, the orientation preserving group, the group of automorphisms of R, and we took a subgroup Z comma plus. This is a subgroup of that. Sorry, this way, subgroup of that, and we looked at the action of this. What is the action? It means that it is basically equating certain numbers. That is that equivalence relation. We took the action of this on the space R, and we could actually equate and crush this R into an interval 0, 1. What is more, 0 is equivalent to 1. So this gave us the space, which is the circle. So this is a way of manufacturing new spaces from older ones. So the circle, S1 is the circle, is called the quotient of R, is the quotient of R by the group Z plus. So subgroups of the groups of automorphisms actually help us create new spaces from older ones like that. Okay, so groups act. So this is an example of action of Z plus on the space R. So groups act on spaces to create new spaces. Okay, so that was what I had to say, and so I will stop here with this example. Thank you. Are there any questions?
Thank you so much, sir.
You're welcome, Sweksha.
Sir, can you share these notes?
These notes? Yeah, I can share. I will figure out how to print them or make a PDF and I can share them. Yes.
Yeah. So, sir, you can mail to me.
Yeah, sure. Okay.
Sir, can you suggest some reference for
yeah, sure. So for these group actions, you can refer to basic topology by M.A. Armstrong. In particular, you can look at chapter 4, section 4, I think, section 4, which is titled Orbit Spaces. Okay, and if you are a slightly more advanced student who can, who are willing to look at group actions in general, there is a reference. This is called geometric group theory. By Clara Lowe. So this is an undergraduate text. However, I mean, do not underrate it just because it's an undergraduate text. There is a lot of content to it, and it gives you a good introduction to this group actions on spaces to create new spaces. Not only that, there is much more over there. Okay, so these are two references.
Okay, thank you, sir.
You're welcome. Any other questions? Yeah, okay. I thought there was a question. Okay, so if there are no questions, maybe we can end here.
So, thank you everybody for joining this session. Thank you so much, sir, for your time and benevolent effort. I hope we all had our piece of cake, piece of this lecture, piece from this lecture. There's a feedback form in the description, in the message box that we've dropped down. And I request everybody to please fill it up for the participation certificate. And thank you, sir. Good night.
So, sir, can we end the session?
Sorry?
So, can we?
Yeah, sure, please. Yeah, I'll be glad.
Thank you so much, sir, once again.
Yeah, thank you. You're welcome. You're welcome.